Hello, everybody. Thank you very much for joining us today. I am Kim Duck, and one of the geomechanics specialists at Rocscience. Currently, I'm also the project lead for RS2, and I am also responsible for the finite element algorithm in RS3 as well. And for the webinar today, I will talk about different approach using the site for the site response analysis, and then I will also cover the topic of the features available in RS2 and RS3 for the nonlinear dynamic analysis. That will cover the formulation of damping, time step, boundary condition. I will also talk about two very useful tools for dynamic analysis, which is the dynamic data analysis as well as the natural frequency analysis. And at the end of the webinar, I will show a live demo for the 1D site response analysis, 2D seismic response of a tailing dam, and finally a 3-dimensional machine foundation dynamic analysis. So one of the approach for the site response analysis is the linear elastic analysis. And in this approach, the materials have a constant young modulus, and it has a very infinite strength, and that approach is very simple and has a very limited use. Another approach which is also very popular is the equivalent linear analysis, and we often get a lot of questions from our customer that do we provide that approach in our programs. So the question is no, we don't directly provide, but from the after this webinar, you can certainly do an equivalent linear analysis using our programs. So let's talk about this approach. In this approach, we have the constant stimulus for each part of the time history. It means that, for example, at the initial, we will assume an initial value for the shear stiffness, and then we run one pass to the time history with the constant shear modulus. And after that, we got the big shear strength here at gamma 2, and then we will get the equivalent shear stiffness, a new one called Z2 here. And then we run another pass and get another value of the peak shear strength and get another value of the peak shear stress. And the process keeps iterating until the differences in the shear stiffness is smaller than a tolerance, and that when we accept the solution. So from the approach, we can clearly see there are some disadvantages of the methods. The first one, because the methods use the constant shear modulus, and that's why we might have the spurious resonance, because the shear modulus will constant. And because that spurious resonance phenomena rarely happen in real life, because the shear modulus is completely changing in the simulation. And another disadvantage of the method, because it's use the total stress analysis, and one of the problem that involves poor water pressure will have difficulty to deal with. For example, it is very difficult to model the liquefaction using the method. And another disadvantage of the approach is that it is a curve fitting for the plastic material, and that's why there won't be any permanent deformation. However, it's still widely used because of the simplicity and the availability of the material properties. And the approach that we use in our program is nonlinear analysis methods. And in this method, the material properties are calculated based on the current state. So as you can see here, it is a very simple nonlinear cyclic models. As you can see here, the 2 points, it corresponds to the current state of the stress and strain relationship. And at the beginning of the cyclic load, this stress and strain relationship will follow the curve called the backbone curve, and then at its reverse the direction of the shear strength, the stress and strain relationship will follow the cyclic stress strain relationship, and this will keep going on until we got to the normal stress ratio. Another properties of the approach is that we can use the effective stress analysis with the pore water pressure, and that's why we can easily model the exit pore water pressure buildup using this approach. And of course, you can use many advanced logic models to model the more realistic behavior. The nonlinear dynamic analysis in RS2 and RS3 can be activated in the project setting, as you can see here in RS2 and RS3. And this is worth noting here is that the dynamic analysis model in RS2 and RS3 is automatically included in our programs, and you don't have to pay any additional fee to use the module. And to follow up, I will cover the features of the dynamic analysis in RS2 and RS3. I will talk about the formulation very briefly, as well as the time step, damping, loading, and boundary condition that we provide for the user. And then we will also cover the dynamic data analysis and the natural frequency analysis tools. And I will also cover how to view the dynamic results in RS2 and RS3. And here is a very simple formulation for the dynamic analysis when we have the mass matrix multiple to the acceleration vector plus the damping matrix multiple to the velocity plus the stiffness matrix multiple to the displacement plus force, and everything needs to be in balance and is equal to 0. We use Newmark time integration for RS2 and RS3. And we use beta equal to 0.25 and gamma equal to 0.5. And using these parameters, the simulation will be unconditionally stable. You can select any time step as possible. However, the time step still be controlled by the accuracy check of the programs. After substitute the time integration into the equation that I just showed in the previous slide, and I rearrange it, we will have the right-hand side as shown here. And this right-hand side will be updated for every time step or for every iteration if the materials is nonlinear or we have the plastic material in the simulation. And the left-hand side matrix, we call it the effective stiffness matrix. And this matrix will be updated for every time step that change because it's related to the delta T right here. And it can also need to be updated if the material is plastic or we use the tangential stiffness. And here is the option for the time step in RS2 and RS3. We have 3 options for the user. The first option and also is the default option of RS2 and RS3 is the auto option. And if you select the option, the program will automatically calculate the most appropriate time step. And it depends on the duration of the stage and it also depends on the dynamic load. And the time step will also be adjusted based on the accuracy of the solution. If the solution does not achieve the desired accuracy, the time step will be reduced, and so on. If the solution achieves the accuracy, and then the time step can be increased to save the compute time. Another option is that user can specify the default length of each time step. And the last option is that the user can specify the number of the time step, and then the length of each of the time step will be calculated from taking the duration and dividing it by a specified number of time steps. We provide two methods of damping in RS2 and RS3. The first one is radial damping, and the second one is the hysteretic damping. And now you can come back to the equation at the beginning. The C is the damping matrix, and in the radial damping, the C will be related to the stiffness matrix, and the stiffness matrix by alpha M and beta K, and it's also related to the velocity of the system. And here is the radial damping option that you can access in the project setting. And to define the radial damping parameter, we can have two options. The first option is to define the damping coefficient alpha and beta. Let's go back to the previous slide. Here, you can see alpha M and beta K here. You can input it, or you can just input the two frequencies and the damping ratio. Then the program will automatically calculate the alpha M and beta K and get into the radial damping. The two frequencies are selected based on the natural frequency of the geometry or structure, or it can also be depend on the input motion. The second approach is the hysteretic damping, and basically it's just the nonlinear relationship between the stress and strain in the dynamic simulation, and we provide a lot of nonlinear formulation in our programs, and by using this nonlinear formulation, you can achieve the same degradation curve as in the equivalent linear method. And that's why I mentioned at the beginning of the webinar that you can also doing the equivalent linear methods in our program by matching this degradation curve with our material properties. And for example, if I use this formulation, and I can match very well with the degradation curve from the equivalent linear programs, and I can also match very well with the cyclic response of the stress and strains. However, pay attention here for the hysteretic damping. When at the beginning of the simulation, when you have a very small strain, it is recommended that you should use a radial damping, but only with a stiffness proportion to accommodate for the energy dissipation when the strain is small. And also the hysteretic damping is not needed when an advanced concept models already accounted for the hysteretic damping. For example, here is the stress and strain relationship of the Manzari and then Valias models that we have in our programs. And as you can see that the stress and strain already exhibit the hysteretic damping right here. A side note here is that you can see that beautiful, nice animation here, and it is provided in our upcoming programs. It's called RS data, and it is at the end of the development, and it will be provided to the user in the next couple months. We also provide a lot of loading and boundary condition for dynamic analysis. For example, you can have absorb, transmit, damper, nodal mass, hydromass, and type of condition. So with all of the boundary condition type here, you can create models to simulate most of the real life problems. So the first boundary condition is the absorb boundary condition. Normally, if you just use the regular static boundary condition, we will have the problem when the wave is reflected back into the main model. That's why the researcher had developed the absorb boundary condition to absorb the outcoming wave from the models so that it won't reflect back into the main model. And in RS2 and RS3, we use the formulation from Leitner and Kuhlemeyer. And here is the typical use of this boundary condition. For example, when you have the source of dynamic is inside of the model, for example, when you have the machine vibration at the surface, or you can have the train moving, or you have the mining explosive inside the main model. And you can also use this type of boundary condition to model the seismic hazard mitigation, such as vibrodynamic compaction or blasting. And to do that, it is very simple. You only need to assign the absorb boundary condition to all of the external boundary except the free surface. We also provide the damper boundary condition, and it is similar to the absorb boundary condition, except that you can input the coefficient. For example, here in 2D, you can input X and Y direction, or in RS3, you can input X, Y, and Z direction. Another very important boundary condition is the transmit boundary condition. It is very similar to the absorb boundary condition, except that beside absorbing all of the outcoming wave from the models, it also applies the motion from outside the model to the main model as well. And so the typical example of the application of the boundary condition is when you have the dynamic source is outside of the main model. For example, when you want to model the seismic event, of course, you will want to apply the earthquake motion at the bottom of the main model. However, we also want to account for the wave going into the model from the part of the soil that was not included in the main model. And for this particular problem, it's also very simple to assign the boundary condition. You only need to assign the transmit boundary condition on the two vertical sides of the main model. And if the combined base were used, you also need to apply the absorb at the base. However, if you use the rigid base, and then you don't have to do anything, just apply the motion directly on the boundary. We also provide a nodal mass, and it's quite simple. You just select the nodes and then specify the additional mass, and the program just add that mass into the node. Similar to nodal mass, we also have the hydro mass, and the hydro mass condition will add extra mass caused by the hydrodynamic force on the surface. For example, when you want to consider the dynamic force of water on the upstream face of a hydro dam during an earthquake, and the formulation is based on the paper from Westerler. We also provide a time boundary condition, and it can be used to create a soil column to model the 1D side response. It can also be used to model the free field effects. However, in order to use the time boundary condition to model the free field effects, we need quite a bit of manipulation of the models. So it is not recommended to use the time boundary condition for the free field effects. You can just use the transmit boundary condition directly. We also provide one of the dynamic load type that is necessary for dynamic analysis, such as force. You can assign the line or distributed force, or you can assign at the displacement, velocity, or acceleration. However, when you apply the velocity or acceleration, you need to pay attention to the property of the input motion. If the input motion is outcrop, and you need to use a combined base, and if the motion is within motion, and you should select the rigid base. We also provide other features such as import and export, which is very popular of our customer. And the third tools that I present today for the dynamic analysis, the dynamic data analysis. Using the tools, you can analyze the input motion property, such as amplitude spectrum. You can see here on the image. You can also analyze the response spectrum of the motion, and you can also see the area intensity. Besides that, you can also do calibration on the input motion, such that you can filter the high frequency noise from the motion as well. Or you can use the baseline correction to correct the error from the machine or the error from human. And here is the snapshot of one of the example that we did for the input motion. And you can see here the red line is the original input motion, and you can see clearly here that something is not quite right. The equipment either tilted or we have some error during the earthquake. And after applying the baseline correction here, you can see the blue line is more or less more appropriate. The second tools that we provide for the dynamic analysis is the natural frequencies analysis. And the frequency analysis is very popular among structural engineers to design the environmental forces frequencies. However, for the geotechnical engineers, it's also very important because it can be used to supplement to determine rayleigh damping coefficients. And using the tools, you can also have an interactive chart to see the effect of alpha and beta over a range of frequencies, because sometimes you want to have a constant damping ratio over a range of frequency. And in order to do that, you can just adjust the alpha and beta and see the effect of them on the range of the interested frequencies. And of course, you can also use RS2 and RS3 to generate the exit flow pressure. In order to do it correctly, you can use the loosely coupled model based on the paper from Martin, or you can use many other advanced constant models that we have in RS2 and RS3, such as Manjari and Danfilas, Bowling circuit model, Rocscience model, Hartling softening models. We have a lot of them. And in RS2 and RS3, liquefaction triggering evaluation, damage during and after earthquake can be done in just one analysis. And another feature that we have is time query. For the dynamic analysis, it is very difficult or almost impossible to save all of the results for every time step. And that's why we need to specify a point so that the result will be recorded for the duration of the dynamic stage. So, and you can add a temporary lines to collect the time-dependent data at various points along the line, or just you can just select a specific point, and the program will collect data at that point. And you can record the all of the data, such as displacement, velocity, acceleration, stress, strain, and water pressure. And so for the first example that I'm showing today is the 1D side response comparison. So normally when an earthquake motion will recover, the equipment normally will at the surface or at some certain depth. And when you want to model 2D or 3D dynamic models, the depth of the models will depend on the structure, it depends on the geography, it might depend on the specific needs from your project. And sometimes the depth from the 3D or 2D models are not at the same depth of the recorded motion. And in order to get the earthquake motion at a certain depth, we use a process called deconvolution, which means that we can get the earthquake motion at a particular depth from the recorded motion on site. So let's say here, we see on the surface, we have the recorded motion, and which will be used as an input to the 1D side response. And then we can specify the output motion at some certain depth. And it can be within motion, or it can be outcrop motion. And depend on the motion property. If the motion is within, and we can use the rigid base. And if the motion is outcrop, we will use the combined base. Having that motion, we will apply to the base of the model, and then we can perform the dynamic analysis and analyze the response of the model under the seismic event. Now it's always a good practice to create a soil column in 2D or 3D programs and use that incoming motion at the input and get the motion at the surface of the soil column. And then we compare the motion at the surface from 2D or 3D programs and compare it to the recorded motion. Another application of the soil column is when you want to match the material property in the nonlinear approach with the equivalent linear approach. And here's the one of the 1D side response comparison between our program RS2 and another 1D program is called deep soil. Here the soil parameter has jump equal to 2.6, Poisson ratio equal to 2.4, unit weight of 24, and from that we can calculate the shear wave velocity equal to 1948 meters per second. The height of the model is 300 meters, and from that we just use the analytical solution to get the first frequency equal to 1.623. And if you look at here from our natural frequency tools, you can see that we got exactly the same for the first frequency. And as suggested from Kramer, the second frequency that we used for the ready damping will be equal to 5 times of the first frequency. So here it will be equal to 8.115. And we use the ready damping of 3% for the models. And having that two frequencies and their damping ratio, we just input those parameters into the project setting. And here is the result that we got from the simulation. We compare our result with deep soil output, and you can see that there's hardly can be seen any differences. The same thing happened for the velocity and spectral acceleration as well. Now let me open the 1D models in our program. And also for dynamic analysis in RS2 and RS3, we always need a good static model to begin with. It means that for the initial stage, the model is always static and or is always a static stage. And then we can assign the dynamic condition on the second stage of stage after second stage. And to model the soil column, I only need to assign the transmit boundary condition on the two sides of the column, and we can apply a load at the bottom of the soil column. And depend on the type of motion, if the motion is outcrop, we just use the combined base, and if the motion is rigid, and then we just apply directly to the bottom. Alternatively, instead of applying the transmit boundary condition, we can also use the tie boundary condition to model the soil column effect. Now let's go back to our slide. The second example that I present today is the 2D seismic analysis of a tailings dam. Also, again, these models will form a good static model to begin with. And here is the material property of the tailings dam. We have the tailings materials right here, and rock fields here to stabilize the damping tailings material. And then we have a dense to very dense silty sands, and we have a bedrock at the bottom. And we want to analyze the response of the tailings dam under a seismic. And we also want to see the poor water pressure generation during the seismic event. But pay attention to here, that rock field. We cannot have any exit water pressure build-up in rock field. Also for the dense sand, because under the cyclic loading, dense sand will exhibit dilated behavior. So we don't have to simulate the exit water pressure in that layer as well. So the only layer that we need to pay attention for the exit water pressure is the tailings material right here. And in this example, I will show you how to do a dynamic data analysis, and I also show how to run a natural frequency analysis in RS2 as well. And I will also assign the boundary condition for this particular dynamic simulation, and the seismic load application, of course. And I can also show you how to view the dynamic results in RS2. Let's open our RS2 program. Let's open the static models. And again, like I mentioned, we always need a good static model to begin the dynamic simulation. And in order to create a good static model, we need to start from simple first. We create a very simple geometry using the elastic material and make sure that the result makes sense. And then we will add the complexity as the models become more complex to achieve the design properties. And the first step for the dynamic simulation is we want to run the natural frequency analysis of the model to get the correct parameter for the gradient damping. Now let's turn on the dynamic analysis module. Now click OK. The program will ask you to increase the number of steps to 2 because, as I mentioned before, we only need a first very good static models. Click one, OK, and go to mesh. Reduce the mesh size to 50. Click OK. Now we have a very coarse mesh here. Open the natural frequency. Then let's surface another pulse. Then natural frequency. And now we can run the frequency. Now we change the default value to 0.1 and 10, and then we press compute. Okay, now we can see the result from the natural frequency. For the drilling damping, the most important frequencies is the first frequencies, and that's why you can see here we got the first frequency equal to 0.399. And I know that some of you will have a questions. Why do I need to make a very coarse mesh like this, and will the result will change if we use that coarse mesh, and can it be reliable? So actually that is the trick that I want to show you today as well, because for the natural frequency, we can use very coarse mesh and we still get the same result. Now let's open a model with a very fine mesh. See like this, and go to the natural frequency and we see the result. And so the first frequency of this model is 0.3986, right? 0.3986. Okay. Now we go back to the model with the core mesh and see what we have. Okay, we got 0.3991. So the difference is even less than 0.1%, and that is very good accuracy that I can think of. Now let's close this. And having the first frequency, now we're gonna move on and create final dynamic models. Now let's set that seismic. Okay. Now the next thing that I want to show you is the dynamic data analysis tools. Let's open this. And in this tool, we also provide a lot of example of the earthquake and a different record as well. However, for this particular demo, I will just open a motion from a text file. In this tool, it can also convert if the text file had a different unit system than the current system. However, because our text file had the same unit system, so I just click OK here. And then you can see that we can analyze the property of the input motion. For example, you can see the amplitude spectrum of the acceleration. You can also view the velocity. You can see the response spectrum as well. You can also see the effect of the damping on the response spectrum. You can also see the error intensity. Now let's go back here and change the input to acceleration. And as I mentioned before, we can see that the input motion has something happening here. Let's go to the filter spectrum. We want to filter the high frequency noise. That's rectangle here, right here, and the baseline correction. Just accept all of the default value from the programs, and we click apply. And see here, the filter motion is look much better now. Let's click OK. Now we can define a dynamic load. So let's select acceleration, go to define, and then we want to use the data we just analyzed, and select this. See that we have it right here, and we click OK. And because the motion is the outcrop motion, so I will select the combined base and I click OK right here. Now we go to the project setting, go to the stage, and we will add 2 more steps to see the full picture of the result during the simulation. And I will assign the dynamic frequency. The first one is 0.399, 0.399. The second one will be 5 times of the first one, and we will get 0.5. Damping ratio is 2%. Click OK. And now we don't want this core mesh anymore. Let's put it 3000. And that's here is good model. And now, as the dynamic simulation going on, we don't want any of the static boundary condition on the model anymore. So the first thing I want to do is I'm gonna free all of the static boundary condition, and then I will only assign the static condition for the first stage only, and that can be done by using the stage factor for the displacement. And we do here, click apply, and let's double check to see. Okay, now you see that at the dynamic stage here as highlight, we don't see any static restraint anymore, so it's good. Now we go to the dynamic tab, and we're gonna assign the dynamic boundary condition to the models. And as I mentioned before, for the particular type of problem, we want to apply the transmit boundary condition on the two vertical boundary condition. Okay, and then we can apply the absorb at the bottom because we use combined base, right? And then we will have dynamic load at the bottom. So now we want to see the exist parameters build up. The first thing we want to consider is we need to select the appropriate concept models. In RS2 and RS3, we have a lot of dynamic models, not a lot, we have 3 of them, but you can also use a lot of other advanced concept models such as Rocscience or stopping happening model or Barcelona as well. But for this demo, I will use the FEM model. The reason I use the FEM model because it's very simple. It's based on the Martin paper, and it's gonna use 4 parameters to fit with the experiment data. However, another paper by Bird, they suggest another approach that is very, very useful for me, in my opinion. That is, it only requires 1 additional parameter comparing to the more column models, which is the number of locales N60. And here we just accept the default value of the models. Now we want to see the result, and probably we need to add the query point. So let's add the first query point at 90 and 14. And the second one at 110, 35. And then we click done. We also want to add a time query line. And let's start from the surface is 125, 96, and going down to 125, 11. As you can see here, it had the 10 point along the query line, and each of the point will have the whole history of the simulation. And since we want to get the pool water pressure, it is very important that you need to turn on the undrained behavior of the material starting from stage 2, which means that starting from the beginning of the earthquake. And that's it. You already create the dynamic model for starting from the very good static models. I mean, again, it needs to start from a good, stable static model. And just to save time on the webinar, let me open the result directly. Okay, and you see here the pink light here is the groundwater level. And let's go to the pool water pressure here. So in the tailing dam, you will have the zero total head on the left hand side, and you have the 46 meter of total head on the right hand side. And here is the poor water pressure distribution in the tailing dam before the earthquake. Let's see how it changed during the earthquake. At the first step, which is after 1 second, you see a little bit increase right here. And then at the 10 second, you see more. And at the end, it's clearly developed a acid poor water distributor. Now you can graph and see the poor water pressure distribution increase by time. See that nice graph of the poor water pressure buildup. The poor water pressure will increase until after 30 seconds, and then it won't increase anymore because it's only achieve the maximum irrecoverable volumetric strength. Okay, so now let's go back to the slide. The last example that I want to show you in this webinar is the 3D machine foundation dynamic analysis in RS3. And again, using the, I also start from the very stable static models, and I will apply the dynamic load to the foundation of the machine right here on the screen. And in this demo, I will also cover the natural frequency analysis, and I will also show another approach to determine the two different frequency of the railing damping. And I also show the boundary condition assignment for this typical problem when you have the source of dynamic inside the model. And I will also show you the result in RS3. Let's open our RS3. Let's start from the static model. So similar to RS2, the first thing that we need to do in the dynamic analysis, we want to run the natural frequency analysis. Now let's set as natural frequency. Okay. And then we also need to turn on the dynamic function. Just accept. Then the same thing happens. It will ask us to go to the stage setting and add another stage. So let me put 0.7 here. And using the same trick in RS2, I will reduce the number of elements in the mesh. It can be done by just input a very large number here. And then we're gonna run. We're going to do the same range of frequency here. So the first frequency that we got from the natural frequency is 0.777. I also have a final mass of the models, and we got to have the same natural frequency as well, but because of time restraint, so I will skip that step. Now let's set the model as another name. Now go to dynamic, and we want to import it from the text file as well. And we can select the space at the separator. Click OK here. Another approach that we can use to determine the ray damping is that the approach consider both natural frequency of the model as well as the natural frequency of the input dynamic load. And I will show you right now. Now let's see the natural frequency of the motion. You can mouse right here, and you can see that the maximum or the dominant frequency of the input motion is approximately 5, or actually it's 5. And now go back here. Okay. Now go back to the project setting and go to dynamic. Change here. And the first frequency is 0.77. So in order to get the second frequency, Hudson, in one of his papers, suggests that the second frequency is the closest odd number of the ratio between the motion frequencies, in this case 5, and the first frequency of the models, in this case 0.77, multiple to the first frequency. So in our case, we have the ratio between the motion, the frequency of the motion is 5, divided by 0.77 is the natural frequency of the model. We got 6.47, and the closest odd number is 7. We multiple 7 to 0.77, and we got 5.39. And we just use the default value of 2% of damping ratio right here. Click OK. Now we want to add a couple of stages. Zero point 73, 75, 5. And similar to RS2, we also need to remove the static constraint right here, because if we keep that, the outcoming wave will be reflected back into the model and causing problem. Now we only want to assign the solid constraint for the first stage only. Let's select all the faces. Except the bottom. And we're gonna set the detachment to fixed and remove at the second stage for these faces. And we do the same thing for the bottom, except that we're gonna fix everything. And also remove at stage 2 as well. Now let's double check to see if we applied correctly. Okay. The next step, if we go to apply the boundary condition to the model as well. First thing, we need to select the face. And this time, we also select the bottom face as well. And we want to apply the absorb boundary condition to everywhere except the free surface of the model. Now let's go and see if we apply it correctly. So symbols right here. Okay, and the initial stage we don't have that dynamic, and on the second stage we have that. And next we will assign the dynamic load here. The same thing, we need to select the face here, and we just add the dynamic loads, which already designed. If you want to view it, just click here and show symbols right here. And you can definitely see that we have applied the dynamic load right here. And that's it. You already create the 3D dynamic model from a static model in RS3. And if you use that, and you click compute, and you will get the result. But because of the times constraint again, we need to add the quadrilla as well, so that we can see the dynamic result. So here, let's go dynamic. And we're gonna add the query line. It's gonna go from the top of the foundation to the bottom of the models. So freehand here, check the input, 5327, then 9.7 is right at the top of the foundation. And the second point will be at 5327 and 57 and minus 40. Click down. And we only need 10 locations along the void. As you can see right away that the curly line going from the top to the bottom. And that's it. That finished off the creation of the dynamic model 93. Check we save, and did you compute, you're gonna get the dynamic result. But let me just open the already compute models. So in order to see the effect of the dynamic load, let me set the reference state to the initial stage and just hide the exterior contour. Go to the ice displacement because we apply the force in the ice direction, right? So you can see that the wave transmit down to the bottom of the model. So here and here. And let's go to the query line. You can also see how the specific point changing during the dynamic loading of the foundation as well. And that's conclude the webinar. And thank you very much. And looking forward to see you on our next webinar.